So, I hope we're all ready for the last of the train. It's got pictures, I hope. That's it for the pictures.
Do we have sound? Yes.
Yeah, great. So it's my pleasure to introduce Lou Kauffman. We'll talk about a Penrose coloring formula for non-planar graphs, state model, graph theory, and topology.
Thank you. It's a pleasure to be able to talk to you. I'm going to talk about a formula of Penrose that goes back to a paper of his. So let's look at the paper, but before I do, I wanted to mention that in this Escher drawing of the this rather impossible cube, he's drawn a little diagram here with the card crossings that seem to be culprits written with circles. And it's the very same convention that we use in knot theory for crossings that are suspect. They could be suspect in various ways. They might be suspect because the object that you're projecting into the plane doesn't really fit into the plane, or they might be suspect in that we don't know which way they go. So, it's interesting that he used that convention in his work. Anyway, I'm reminding myself here of a paper that Penrose wrote a long time ago called Applications of Negative Dimensional Tensors, I think around 69. And that's where we're going to start. And I want to remind you, if you haven't seen this paper before, of the sort of thing that he's doing. He makes diagrammatic indicators for what might be tensors, or they might just be matrices with many indices, some up and some down, or these symbols here might just be symbols for the diagrams over on the left, indicating that they could be connected to other things and so on. In which case, you might be encoding graphs with various kinds of vertices by using tensor notation. And these days, I think people call things like this tensor nets. The term somehow blossomed in the physics literature in the last few years, but it goes directly back to Penrose's idea of making a language out of abstract tensors in this way diagrammatically. And if you had something that was going around in a circle and had no structure on it, no matrix structure, then you think of this as the identity. You think of this, you think of a line which has nothing on it as a Kronecker delta, A and B on the edges of the line, top to bottom, never mind the connection back, would be a delta AB and would be equal to 1 only when A is equal to B, but if you turn it all the way around and come back, well then A is equal to B and you have delta AA. But in his system, delta AA might even be negative, and we'll see why. In any case, here, if this were the identity matrix, then it would be the dimension of the identity matrix. If it was a 2 by 2 matrix, you would get 2 because you were summing over 2 indices. And if it was an n by n matrix, you would get n. So this is a dimension, and that's why this paper talked about negative dimensional tensors. Now, if this, there, sorry. Okay, and then here's another page from the paper, and I'm going to stay on this page for a few minutes, because as you see, he starts talking about, well, you could have up indices, you could have down indices. You would like to have something like this happen, which is a little bit of topology, that a wiggle like this should cancel out. And what would it mean in terms of the tensors for a wiggle like this to cancel out? I'll use the blackboard and explain that. And then he created a system which he called binars, which had the property that whatever tensors these were, they added up to 0, and there's a reason for that. And then it turned out that this was very topological, and that it was a kind of flat diagrammatic topological basis for what he called spin networks. And while this is not the place where the talk actually goes directly, I want to talk about this slide a little bit and tell you what it was that he was doing. So he had the following tensors. This is epsilon upper AB, and this is epsilon lower AB, and epsilon, two indices, epsilon 0, 1 is equal to 1, epsilon 1, 0 is equal to minus 1, epsilon 0, 0 equals 0 equals epsilon 1, 1. And you can think of epsilon as this matrix, if you like. What did I do? I'll put the minus 1 down there. Yeah, okay. That's epsilon, anti-symmetric tensor, very elementary one. And the reason he was interested in this tensor is because of the following formula. If you take M is a 2 by 2 matrix, then you will find that M epsilon, M transpose, is equal to the determinant of M multiplied by epsilon. That's a fact, you can check it. And of course, I might have gotten it wrong by putting the wrong sign in that order, but you can check that slide. And that means that the group SL2, C, if you like, or Z, whatever, wherever the matrices are, is equal to the set of M 2 by 2, such that M epsilon, M transpose, is equal to epsilon. You want the set of matrices of determinant 1. And so you can indicate them that way by an invariance under this action. And he was interested in that. His networks that he was studying were tensor networks that were related to SL2, and that for the sake of studying angular momentum. These are topics that I'm not going into in the talk, but the point was that he wanted to do diagrammatics for these networks, and he had quite a lot of complicated diagrammatics related to angular momentum and his idea of creating space-time from the networks. And so he wanted things to be as good at the bottom as possible, and good meant topological, because he would like to draw a diagram and not worry about topological pushing of it around back and forth. And he was aware that if he had something like this, in fact that's it, it wouldn't be equal to, well, I'll tell you what it is equal to. It's equal to minus this. That is, I have an A here and I have a B here, and I have an index in here, and I'm summing on that because an index which has no free end, a line with no free end, is a repeated index in the tensor, right? And so you would be summing over that. And you would like this to be equal to a Kronecker delta in the best of all possible worlds, but it isn't. It's equal to minus the Kronecker delta. I won't calculate it for you, you can check. So what he then decided to do was to see what would happen if he modified it a little bit. So what if you were to multiply the down one by the square root of minus 1, and the up one also by the square root of minus 1, obtaining two new diagrammatic tensors. So that means this is the square root of minus 1 times an epsilon with down indices, and similarly. And then, of course, we just proved it, modulo my lack of calculation, that this will now be equal to that, because the square root of minus 1 squared kills the minus 1 here and makes it topologically invariant under this. So that was the beginning, and that was, I believe, what he chose to do, and then he found that he had done better than he could have imagined, and his planar networks were working very well. And what I mean by that is that he could also check that if he had two, oh, I forgot to tell you that he had to do one more thing to make life very good, and that is he replaces two lines crossing by a minus sign times two lines crossing, one extra minus sign whenever two lines cross. And then the following identity takes place. But I ask your permission to let us figure out what this identity is. This identity, without any niceties, is this, and you're going to see that this is true by just staring at it. That if I have an up epsilon and a down epsilon in this order, then it's the same as taking two Kronecker deltas minus crossed Kronecker deltas, and I have not done this extra change yet. This is just about the old language of epsilons. Is this obvious? Sure, try it out. 0, 1, and 0, 1, what will you get? 1, 1, right? And over here you have indices 0, 1, 0, 1, 0, 1, and 0, 1. And this is 0 because Kronecker deltas go to 0 when they aren't equal top and bottom. And so this goes away. And this one gives you a 1. That gives you a 1. This gives you a 1. It's true. And what happens if I switch an index? 1, 0. Then this one goes out, and this one gets a minus sign. 1, 1, minus sign. And that gave you a minus sign, so it worked. And then what would happen if you had multiple indices the same, like a 0, 0? Well, then everybody will be 0, but what if they were all the same? Maybe you could start to worry that a Kronecker delta would switch on if they were all the same. So I'll try them all the same. And this is 0 because when the thing is repeated on an epsilon, it's 0. But this is 1, 1, 1. But this is 1, and 1 minus 1 is 0, so it all works. Okay? So this identity is true. And this is the identity at the bottom of his tensor networks that he's working with. But what is he going to do? He has decided to make this change. And if he makes this change, then he's going to be turning this into root minus 1 and root minus 1. And so that will turn this into root minus 1, root minus 1. Then that's going to put a minus sign on everybody. So that will put a minus sign here. And then you'll have, you will make this into a plus sign. But then he changed that sign. So it stays minus, and that's what he called the binary identity. Up there on the slide, you see it written equal to 0, but I have written it as one thing equal to the minus of the other two. Same. Then what about the loop? Well, the loop is really a contracted tensor where you're summing over A and B here, right? And there's a square root of minus 1 top and bottom, so this is equal to minus square root of minus 1 squared, the result of doing this. And what will you get there? Well, every time you have an epsilon that contributes, it contributes the same thing, top and bottom, so it gives you 1. Over across the dimension of the 2 by 2 matrix, it gives you 2. So you get minus 2, minus 2. And that's why he titled the paper Negative Dimensional Tensors, because the fundamental binary tensors that he had found his way into were negative dimensional, okay? And then there's a little more to this story, which is that, as I said, it's more topological than he could have imagined, and he saw this much because he's working with the planar networks. He saw that given all that convention, then this will be equal to this, and this will be equal to this, and this will be equal to this. Maybe I should draw it up where it makes some sense, but it doesn't really matter which way I drew it. All these things will happen nicely. so that the entire system ends up being invariant under what are called the Reidemeister moves by topologists, but flat ones, not the over and under woven ones that non-theorists use. So by a certain serendipity of trying to make his networks topological, at least under this zigzag, he found his way into a collection of networks which he calls the Wiener calculus, which are fully topological in the flat sense. And this actually is an exact precursor to what I call the Jones polynomial bracket model, and that can be thought of as a generalization of his Wiener calculus from this point of view. So I thought I would digress in that direction at the beginning of the talk. The talk could have been about how all that works and to continue on in this direction, but I wanted to talk about the coloring, so I'll stop here. But if anybody is interested in hearing the rest of this story, I'm happy to tell more about it. You might wonder, well, why wouldn't a topologist reading his paper in 1969, let's say, see that there was all this topology going on and it ought to immediately generalize to woven things? At least in the case of this topologist, it looked hard to understand at the time, and it wasn't clear that this pattern was in there. Maybe somebody else wiser in a different world might have seen that. I don't think we need this slide, but you see the sort of interesting calculations that he did in his paper. Oh, we do need this slide, I'm sorry. This is the beginning of the story that I'm actually telling you for the rest of the talk. Look up there at the top, and you see another epsilon. This is a 3-index epsilon now. And he's put an I on it already. So epsilon ABC is running on 3 indices, and epsilon, let's say 1, 2, 3. And epsilon 1, 2, 3 is 1. And if you do any transposition of in the permutations of 3 things, it's changes sign, okay? So epsilon 1, 2, 3 is 1, epsilon 2, 1, 3 is -1. If any 2 indices are repeated, it's 0. And for good reason, similar reason as this kind of reason, multiplies the epsilon by an I, and we'll get to that, what the reason is. And then you watch the kind of thing that he says. He says, consider a planar graph of degree 3, cubic planar graph. We can associate with it a certain contracted product of epsilon ABCs, where one I epsilon ABC is drawn at each vertex, a contraction occurring for each edge of the graph, and then you would get a number out of the graph. So the graph is a little tensor network. There's an I epsilon ABC at each vertex, and they have to be equal across where they're connected. So what does that mean? That means that the numbers 1, 2, and 3 have been placed along the edges, where I, J, and K, as I do in the next slide, and they have to be colored in exactly that way, which means that you have to have 3 distinct colors at every vertex, and you have to color the edges of the graph with 3 distinct colors at every vertex. Those are the contributions to his contracted product, sum. It's going to be a sum over all possible choices of index, such that this is true, which means that we're going to sum over all proper colorings of the cubic graph, where proper coloring means you have 3 colors, and you're choosing in such a way that you have 3 distinct colors at a vertex. That's the coloring problem that I'm thinking about here. That's the coloring problem he's thinking about. And then he says this number, remember there's an I in there, and the epsilon does its sign changing. This number is in fact precisely the number of ways of coloring the edges of the graph with 3 colors, so that 3 distinct colors occur at each vertex. So it counts the number of colors. For example, here I'm using I, J, and K. So ijk counterclockwise gives you plus the square root of minus 1. jik, one of the permutations, gives you minus the square root of minus 1. So all three cyclic permutations of a given type give you the same sign, and the other three cyclic permutations give you the opposite sign. Here's a coloring of this graph. You can check I have three colors, I, J, and K, at every vertex, and then let's look at some vertex, say this one, and I have here I, J, K clockwise, so it gets a minus sign. And here I have I, J, K counterclockwise, so it gets a plus sign. So there are all the square roots of minus 1 decorating the vertices, and we take their product and we find by some interesting miracle, it's plus 1. So what we want to see a proof of then, and then generalize it, is why it is that this product of square roots of minus 1, defined in this way, will always be 1 whenever you have a coloring. And if you prove that, you can try proving it as an exercise while I digress a little bit in the next few slides. You will approve Penrose's result. Yeah. Okay, so now the map theorem, the four-color theorem, is equivalent to a connected plane cubic graph with no isthmus is properly edge colorable with three colors. And consider that I keep changing my color designations. I hope it doesn't bother you. I'm going to use red, blue, and purple. I like to think of purple as the combination of red and blue. And here's the coloring of this graph, red, purple, and blue. And I write it factored as red and blue here. And then I draw loops. Blue continues through the purple because it's factored into red and blue, and a red loop which goes here. The loops I've drawn, of course, are alternating loops in the graph, red, purple, and blue, purple, and of course there's also blue, red. But in this system that I'm using, I can concentrate strictly on red and blue loops, and the purples occur when the red and the blue loops meet one another. So then you see that coloring the graph is the same as drawing a system of red curves and a system of blue curves on the graph, so that blue curves never touch one another, nor the red curves touch one another, but blue and red will share a bit of boundary sometimes at trivalent vertices, and then continue on crossing. Right here, blue crosses red, or red crosses blue, depending on which way you look at it, or bouncing in the sense that blue comes down, shares a bit of red, and comes back. So that's one way of thinking about it, what a coloring is. So here's a slightly faded coloring. Now, the interesting thing is knowing that such things, such systems of blue and red curves like this give you colorings, you can draw an infinite number of doodles of this kind, just not trying to color any particular graph. I just draw a red curve, and then I draw a blue curve, and so on, and stop after a while, and then look back at it, and I have myself, in front of myself, a colored graph. It's colored. So the four-color theorem is saying that when you make these doodles, you are generating all possible graphs, all possible cubic graphs with no isthmus. It's not obvious. Here's another slide with the same example shown here, same type of example. Here's a coloring of this graph, and then I take the circuits, and I find that these are the two circuits, a red circuit and a blue circuit. Okay. Yeah, I need this as well. This theorem, the equivalent to the map theorem, is that a plane cubic graph with no isthmus you have, then there exists an even perfect matching of the graph. So by an even perfect matching of the graph, I mean that there's a perfect matching such that the cycles you get by deleting all of the matching edges are even, all even. And from the side of coloring, this is easy to see because these are all one color, and all these remaining cycles are in two colors, and so must be of even length. And the converse is the theorem, of course. And then an easier theorem, but still a hard theorem, is that every cubic map with no isthmus has a perfect matching. So that's known, and you can start there if you want to think about these things. So there's Peterson, which is not colorable, but it does have a perfect matching. Now, I want to use the perfect matching in the following way. I will choose a perfect matching, and then I will smooth out the crossing there. We're in a digression, you realize, but it's related to what we're aiming for. I'm going to smooth out these two nodes in a pair, like that. Or I could have smoothed them out this way, but I'm going to start by smoothing them out this way. And then I'm going to get a curve or curves, like in this case I got a single curve from this when I made my smoothing. And it isn't colorable if I think that this wiggly line means you shall not be colored the same. Why do I say you shall not be colored the same? Let's go over here. If these are colored differently, I can squeeze them together and get a local coloring of the kind I want by using the third color for the connecting line. And similarly, if they cross over, I can squeeze them together and put the third color in the connecting line. Crossover is when the two colors coming in are reversed in order from the two colors coming out, and parallel is when they are not. So, if I assert that this graph is colorable, and that these happen to be the three C's, then I can look for a coloring of the rest. And so I do, and find that there is one by changing somebody into a crossover. And I didn't do the crossover on this one, so let me hope that I did in the next slide. Well, okay, this here is a puzzle for you. So I stand here with this in front of me, and I would like to color it. But with three colors. But unfortunately, I have all three loops touching one another, and so there's no way to color this with three colors. But the four-color theorem asserts, by what I was just saying, that if you switch some of these sites to crossovers, why then it will be colorable, and I have a feeling that that's shown in the next slide. Yes. There. All right. So here's what I was just saying, that I have these and they won't color. I just labeled them. But if I switch all of them, why then I get three circles and I can color. So another way of thinking about the four-color theorem is that you draw a collection of circles in the plane and some sites, smooth type sites, and ask that the circles all be colored, but colored differently if they touch at a site. And you usually will find it doesn't work, but the theorem says that by switching some of them, it will work. The theorem says. So that's another way of thinking about what four-color theorem means. It's just about some Jordan curves in the plane with some locales there, and you need to switch some of them in order to get a coloring to work. And in this case, it's amusing to see that there's only one switching that does the job. You have to switch them all. And then you get the three circles in a Venn diagram. That works, but not in general any other case. So it just barely got colored in the plane. So you can take this example, which seems to just barely get colored in the plane, and try modifying it off-planar, maybe by drawing a little bit differently the way it's embedded like that in the outer circle. And then you find that this one will not color anymore. No choice whatsoever will color this. And that one is interesting. It's related. It actually is giving one of the fundamental snarks. So we're digressing into coloring and not coloring. There's my snark. Whoop. There's my snark. Watch. There. That's the one I was just telling you about that refuses to color. If we squeeze these back together to see what graph we're talking about, squeeze that here, squeeze that, then we have this graph. And this graph, if you look at it, you might recognize it. It is what's called Isaac's J3. Isaac's had this good idea, Rufus Isaacs, of considering this little gadget here, and he proved that if you put n of these together in this circular fashion, this is the third one, if you put n of these together with ni, why then it's uncolored, it's a sun. And the reason has to do with the way colors come in and colors go out. You get odd permutations of colors going in and going out. And this turns out to be J3. So I just showed you a way you might rediscover J3. And J3 itself, if you collapse this circle to a point, which will still be even uncolorable, gives the Peterson. So that's some of the lore about these things. Now, I want to talk about a way of thinking about coloring that is related to what I've just been talking about, and then we'll get back to Penrose, and that's right for time. So here is an expansion which in its own right doesn't have to do with Penrose, but it's related to Penrose, as we'll see in a moment. I'm saying that all colorings of this graph consist in those where these colors are the same, but, I'm sorry, these colors are different, or they cross over and they're different. That is to say, you would have colors A and B here, and some color C there, and either A and B come out this way, or they come out that way, and we're going to eliminate the edge. So if you try to color this graph, it's the same as coloring this one, making sure these are different, or coloring this one, making sure these are different. A recursion relation which leads you into a flock of coloring problems. Well, you can use it to calculate with if you want to. So for example, K33 here, and I break it like this, and I break it like that, and then I look carefully at what I've got, and then I see that it's really two of these. And then I look at this one and individually work it out and find that there are 6 colorings of this, which have these different, so you can go recursively like that. But then what about Peterson? We want to prove that Peterson is uncolorable. I think my, excuse me a second. My laser beam is getting weak. Okay. Oh, this is still to control that? Or, yeah, okay. Which one? Still weak. At least it's all right. Yeah. Look at Peterson and see what happens. So the logical expansion that I'm telling you about. Oh, well, never mind. We'll just talk. Here's Peterson, and I smooth it or I switch it, right? Now, when I switch it, you see that I have an upper loop and a lower loop, right? And they're told to be different. So that's symmetrical because the inner structure of Peterson is the same. So it says that if you close it on one side and you close it on the other side and ask that those two be different, that's the demand that's being made in both cases. And then you would verify that this gadget here will never do that. It will never give you different colors from one end to the other by a separate calculation, and that proves that Peterson is uncolorable, if you like. Okay? So this kind of recursion in and of itself is interesting to think about, but it has its relative in the Penrose formula. So I think we should find our way in these slides. There we are, Penrose formula, and watch the time so that we don't run over. So here's Penrose again. And I want to think about Penrose in terms of these colored loops, these formations. So let's consider that. Here's a red line, and here's the blue line, and we're going through a bounce or a cross or the other cross. I here have taken the plus square root minus 1 to be clockwise, red, blue, purple, and the minus square root minus 1 to be clockwise, red, purple, blue. So you see that if it bounces, it's plus 1, and there's no problem. We would love it if it was all plus 1, but some of it's minus. And in fact, every time you cross, it's minus. You get two square roots of minus 1, which combine together give you a minus 1. So now you see the proof. You see the proof of Penrose's formula, because you're going to get these systems of loops, red loops and blue loops, and the red loop crosses a blue loop. And every time it crosses, the tensors contribute minus 1 to the number of crossings of the red loop with the blue loop, but we're in the plane, and that is going to be minus 1 to an even number, and therefore Penrose's formula will always give us 1 whenever we're looking at a coloring. An example will help. The text doesn't help, but the example certainly does. Look at the example on the right. Here I have two bounces. I have two crossings and one bounce, right? Two crossings, of course. Each crossing is contributing a minus 1, square root of minus 1 times square root of minus 1. The bounce contributes a plus 1. So the total contribution of square roots of minus 1 is minus 1 squared, because the two curves intersect an even number of times. And this is infinite for any picture that you draw on the plane, and gives you the proof that Penrose's formula does count the number of colorings in the plane. It also satisfies this relation here, and that relation is actually a fact about the tensors. And it's a fact about putting two epsilon tensors together and getting Kronecker deltas and cross Kronecker deltas. It's very similar to what I was showing you here. And very similar to our more general logical identity that I was telling you about before. So it is of interest to compare the logical identity with what's going on in Penrose. But remember, in Penrose, we get an absolute calculation. You just go down by recursion, and every time you get a closed loop, you get a 3. I forgot to mention that that's the rest of the calculation. We're doing it that way because there are 3 colors for one loop. So if you want to use Penrose's recursive method to calculate the number of colorings of something, it goes like this. Suppose I want to calculate the number of colorings of this. Well, then this is equal to the formula applied to this minus the formula applied to this. And each of these are just 3 loops now. This is 3 squared minus 3. That gets a 3. And this is 6, and that's correct. That's how Penrose's formula works. We've proved it in the sense of using the tensor definition, and it follows from the tensor definition that it has this recursive property, and all that's very pretty, and hopefully could lead to more understanding of how it's going to be non-zero on those graphs where it should be non-zero. I'm going to skip this, which has to do with the way the epsilon is related to identities are related to things about cross product of vectors, and also how the map theorem is related to certain properties of vector cross product. We'll just skip that. Penrose formula does not work for non-planar graphs. Here's K33, and we tried it out, expanding it this way and the cross and the minus, but you see, by the same argument as we made before about those loops, one of these is connecting it horizontally and the other vertically, but you get the same graph and it cancels out and gives you 0. What went wrong here? Let's look at what went wrong, and then I can tell you how to fix it, and we'll stop with the help of an eraser. Yes. Take K3
The number of crossing may not be.
I'm sorry?
The number of crossing can be not odd if the crossings.
Yeah, the number of of course, I just wanted to illustrate it, but it's clear. The number of crossings
Yeah,
might be odd
in the plane, yes.
because of the
You use-
non-linearity.
Because the two-dot curve theorem.
Yeah, exactly, right. In fact, I need not do the calculation to see how it's going to work. If you have this guy and you're an extra one, then he's going to get you in trouble because you could have an odd number of -1s between two loops. And I was just going to draw one specific example of that, but we need to do that in the interest of time. So you see that's how it's going to go wrong, but that also tells you how to fix it. It tells you exactly how to fix it if you would like to fix it. Because what we want to do is add a tensor, I think I put it in this, we'll add a tensor for the virtual crossings, the ones that are the immersion crossings of the graph that fell into the plane originally. We will not have to do anything to crossings that came out of expanded design. We just put it on that one, and that one will be plus if these two colors are the same, because that's not a worry about crossing one loop with another. But if they are colored differently, then it'll be a minus. Just put an extra minus sign in there, and then you have a system which will work fine. And then, for some reason, I decided to rewrite that as twice dark dot minus crossover, where dark dot is going to be 0 unless they're all equal. But it comes to the same thing. I could have just left it with the definition over there. And so then you have this revised system, which will calculate the number of colorings of any cubic graph whatsoever. So you take your cubic graph and let it fall into the plane, take an immersion picture of it, and then apply the calculus in the plane with this modification, and you can find out the colorings. Now, that's of interest and ought to be investigated more deeply, but I haven't any theorems to show you about what I can do about colorings of arbitrary cubic graphs yet, but there it is. It exists. It's natural, and that's the basic end of the story. We don't need those, but for example, you can do K33 by watching and keeping track of that extra crossing. Watch your signs and everything will work out, and you can do it recursively using the Penrose type formula. And this is a good place to stop, except to say that the rest of the Penrose ideas, and even these, are related to lots of things in non-theory, and that would be another hour or so. We'll stop at this point.
Thank you very much. And we have time for some questions or comments before supper. No, we got to relax a bit before supper time. So let's thank you again. Thank you.